We'll now pass it on to our speaker, Rashmi Nagpal, who's going to be talking about MLOps. Take it away. Woo!
Thank you, everyone. So I'm Rashmi Nagpal, and I'm a software engineer working in machine learning domain at Cactus Communications. And welcome to my talk. The talk title is Demystifying MLOps. Before delving deeper into MLOps, here is the agenda of the talk. Firstly is the motivation why this topic is relevant, and then I'll explain about the basics of machine learning models. Further on, I'll talk about some of the characteristics of the machine learning problem, and further on, building on top of the previous topics, I'll explain about the framework of the MLOps workflow and further principles of monitoring ML pipeline and couple of resources towards the end. So let's delve deeper into it. First question is, why MLOps? From generating the route to your next weekend hiking plans via the Google Maps or the Apple Maps to recommending you for the latest Netflix shows based on your personal preferences, machine learning has been embedded in our lives so much so that we often overlook it. But have you wondered that how these machine learning systems are deployed in production? The article that you can see on the right-hand side, The Dark Secret at the Heart of AI by the MIT Technology Review, it talks about how the algorithm teaches itself to make the decisions. Are those decisions trustworthy? Are those decisions not biased? What if the algorithm does something unexpected? Who is responsible for the actions? Is it the manufacturer? Is it the data itself, or the data scientist, or the engineers? And also, there are a bunch of other resources by the Gartner and the VentureBeat, which says that, 87% of the data science projects never make it into the production, even though we are training the fancy machine learning models. So let's delve deeper into why it happens. Before delving deeper into it, I'll just talk about the basics of the machine learning models. So you must have often heard about the hype of the AI, and AI, ML, DL, it has been often used interchangeably, but certainly they are not the same. AI is itself, or the artificial intelligence, it's the umbrella on which the machine learning and the deep learning are certain subsets of it. So this infographic states that the AI itself, it's the broadest concept of all, and it gives the machines the ability to mimic the human behavior, while the machine learning on itself, it gives the ability of the machines to learn without being explicitly programmed. The infographic over here shows that you are doing some kind of email filtering, which could be like spam filtering. On the other hand, the deep learning is a technique when the system or the machines extract the patterns within the data itself using some deep neural networks. For example, the handwriting recognition, which is what the infographic over here shows. Now let's understand some of the characteristics of the ML problem. The infographic over here discusses about the characteristics of the machine learning, like how we deal with them. First, understanding the ML-driven business transformation or the use case identification per se is vital. Then we do the data analysis, which has some, like data ingestion pipeline, and then the data which is coming from the multiple sources and in the multiple format. Either it could be the JSON, text, CSV, or like various other formats. It could be structured versus unstructured data set. Then then you are doing all the processing through the data pipeline, and once the data analysis has been done, then in the ML modeling, that data is being ingested. So in the ML modeling, you have the feature engineering and the training as one subset, in which you are extracting what all useful features are required in order to train your model. And further on, you do the training on that particular model after extraction of the features. And then you evaluate the model based upon whatever kind of a classification or whether it's clustering kind of a problem statement of the ML it is. And then, of course, you have to deploy and monitor the model. And also, there is a direct link between the data analysis and the deployment and monitoring, which implies that whenever if you have trained the model on some of the previous data set and now you want to ingest new data set, so the machine learning model needs to train on the new data set. And of course, you need to consider about the monitoring factor, like you need to scale, or you need to see how the model is performing. So basically it helps, like this entire process helps to develop the machine learning solutions to augment or to automate the business operations. Next up is the types of the machine learning models. So there are various categories, and over here I've mentioned like the 4 categories. The first is the learning models. In the learning models, it could be belonging to the supervised learning or an unsupervised learning. So in the previous slide, we have also seen there is ML modeling stage, which has various steps embedded into it. That is, it has the feature engineering, it has the model training and the model evaluation. But all in all, it revolves around which model that you want to use. For example, if the application is to find kind of a malware versus benign files, it will be a classification problem, which is one type of the supervised learning algorithms, which belongs to the first category, that is the learning models. So in the supervised classification or in the supervised, learning, that you have the labelings in the data set. For the unsupervised, we always have an unlabeled data set. So the model has to learn from the unlabeled data set, and there are various algorithms like k-means, EMDB scan, whatnot, and so that these algorithms can be used on the unsupervised clustering. Next category is the statistical models, which includes the inductive and the deductive learning. In the inductive learning, the learner discovers the rules by observing the examples, while the deductive learning is that the learners are given the rules to apply. Parallelly, we have the hybrid models. For instance, we have semi-supervised learning, transfer learning, and ensemble modeling or ensemble learning. And the transfer learning is very vital because it helps in, I'm very biased about the transfer learning is because it also helps in repurposing the, whatever the learned features are there, and also helps in whatever the resources have been used in the previous model which is being trained, and we can repurpose those learned models onto a new data set. And it's very efficient method also because it helps in saving up the usage of hundreds of resources, because training a model from the fresh or from the start often takes like months or days or so based upon how much data that you have. So it's that's advisable and also very much efficient method. Next type of learning is humans in the loop, which involves the active and the human reinforcement learning. So most of the RL or the reinforcement learning concepts are used in the game optimization or for training the robots or for simulating in the synthetic game environment. So this is the one very basic example of the image classification, because I've explained about different types of machine learning models in my previous slide, and therefore it's better to understand through an example one such category of the problem statement or one such category of the model type. So over here you are given an image. You need to identify whether this image, whether this image belongs to which particular category. So as you can see, that what the machine will see is the, it will learn through the pixels, because of course the machine will not ingest the image as a data set, but of course it will be, converted to the vector format. And so conversion of the image to the vector format will happen, and then the data will be fed in that image recognition algorithms, which will certainly give you the confidence score. Here the model is giving an accuracy of 82%, which implies that with 82% confidence score or an accuracy, the model is implying it belongs to a cat. Accuracy is one such evaluation metrics that we use for evaluating our models. Okay, so now since we have understood all these concepts, I'll just talk about one such example. Various stages of the machine learning, all these, how we do the pre-processing, how we do the feature engineering, which I've explained in one of the previous slides. And let's, to make our understanding much more crystal and clear. So in this example, you can see, there is a flight prediction example it is given, that given a data set and the number of features over here, you can see that the airline is there, date of journey, source, destination, route, and, arrival time, and certain other information is definitely there. So you need to determine what for this particular flight, what will be the price. You need to do, the model needs to do the prediction for that. So The couple of lines over here shows that once you have imported the data set, you are just reading the first 5 lines of the data set. You are just checking, like how your data frame looks like. Next up is the pre-processing step. It is basically understanding and finding the patterns in the data, maybe like removing the null values if it arises or if it's there, removing some of the redundant information and transforming the data in which the model needs that. And then data journey is kind of a subset of the pre-processing pipeline. Over here, you can see that I have in the first cell that data dot is null dot sum. Like I'm just finding out what are the values which are present in the data set, which are null, and of course removing some. The second is drop n is removing those null values, and then I'm just trying to understand. Just removing some certain other outliers which are not needed. This process is EDA, which is exploratory data analysis, doing the data analysis, plotting certain graphs, finding the outliers, anomalies, or forming the hypothesis based on our data set. Next up is, again, doing some visualization, understanding how the data looks like, like how it works on. Here, I'm dividing the data set in a certain format. So you need to have, you have certain data. Now you need to divide the data into a training and the testing so that your model will train on a certain data set, will understand, learn from that data set, and then you have to do some testing on that particular aspect. So either you can do the 70-30 or 80-20 rule, which is like training and testing, bifurcation of that data, and then applying some machine learning model onto it. And over here, I've used the evaluation metric, which is accuracy. And so over here we have dividing the data into different, so it's training and the testing over here, like using the train and test split, and And once the data has been, split, we are using this random forest classifier because it's kind of a, what I'm trying to do is finding the best price or, just the price prediction. So once you have used the algorithm itself, you are using some evaluation metrics. It could be accuracy, recall, and F1 score. And then you can see, how your model is performing and make the necessary decisions whether you want to go with this particular model or you want to just do some brute force approach or you just want to explore certain other models which are performing well according to your data. Next up is the framework of the MLOps workflow. Here comes the core of this talk. There is a myth which says that the DevOps is equivalent to the MLOps, but for the machine learning. That is certainly not true. It is definitely there that, MLOps is built on the concepts of the DevOps, but it adds its own flavor to it. For example, the hardware which is required for training the models in intensive, like for instance, you have the larger and the bulky models. It takes certain hours or days to months to train. So definitely it has its own flavor to it. So MLOps basically combines the ML, DevOps, and the data engineering, which aims to build, deploy, and maintain the ML system in production reliably and efficiently. Since I'm coining the words reliably and efficiently, I'll discuss in the upcoming slides what I meant by all these, this technical jargon per se. So, the primary goal of the MLOps is to make the organization or the set of the rules or the individuals collaborate efficiently to build data and ML-driven assets to solve their business problem, and which will lead to overall performance and accuracy, of course, or the transparency will be increased. So because working in silos or, developing functionalities repeatedly can be extremely costly and time-consuming. So next up is this MLOps workflow. This slide basically highlights, what's the workflow of the MLOps look like, which is certainly segmented into various modules. First, it has MLOps pipeline, which implies it has build, deploy, and monitor. In the build pipeline, you can see we have the data ingestion, data training, model training, and the model testing, model packaging, and model registering. For the deploy pipeline, we have the array of others, services, which is application testing, production release, and for the monitor, we have monitor, analyze, and govern services. In the upper layer, if you see in the MLOps pipeline, there is a, huge subset. It has been bifurcated in the build, deploy, and the monitor, while in the which is then enabled by the drivers such as the data, code, artifacts, middleware, and infrastructure. And MLOps pipeline is general, like it's powered by the array of services. It could be a drivers, middleware, infrastructure, and then it crafts the ML-driven solutions. So, like if you use this pipeline and it helps like individuals or the business, they can do the quick prototyping and helps in testing, validating, and deploying the models to production at scale, frugally and efficiently. So we'll discuss every block in detail in our in my upcoming slides, but this is how the overview looks like. The one very vital component before training any kind of a multi ML or like working in the ML or maybe like training the models is what kind of data that you have. Is that the data is good enough for ML? So it certainly does depend upon certain of the parameters. And the 4 parameters to keep a tap on the data are accuracy, reliability, relevance, staleness, or you can say like the timeliness. And so I have, like when I was just always work on building some of the machine learning models. So I have the, like that's kind of a preset mindset that I used to have, that we often have the tendency to approach kind of a complex problem by addressing the symptoms. For example, the model is not performing well. Oh no, what will happen? I need to change the model. Or maybe like it is giving like unreasonable predictions. So what should I do? The knee-jerking reaction in my case is I feel that, like in order to fix that approach, rather than diagnosing the data itself, for example, when the backend system is not scaling, instead of evaluating the efficiency of the algorithm, scaling multiple hardware resources. So we need to go upstream to fix the problem. But unfortunately, we go and try to find the hacky solution. Remember, Tylenol does not reduce the fever always. So the 4 parameters over here which I mentioned is, like the data is good enough for the ML, so it depends upon the accuracy, reliability, relevance, and timeliness. Basically, we need to, recalibrate or calibrate the missing data set and do the label encoding, since the machines will not understand the human language or the text. So all the text, like sometimes needs to be converted in the numbers. And if there is an inaccurate data, then of course your model will perform very bad. And if there is a redundancy in data, then the model will not be able to learn. So it will make unreliable decisions. And if there is an irrelevant information, of course, you have the inappropriate contextualization. And timeliness implies, like if you have the obsolete data, which of course will cost your business time and money, then the predictions are wrong, or the model, there will be a concept which I'll talk in the further slides about the model drift. So, you need to understand whether the data is also which is latest / it. Of course, it has been trained on some past data, but again, since the data is changing, so model needs to learn the changed behavior as well. And next up question is why data ingestion is so important. Since there is a huge inflow of the data in the ingestion pipeline itself, or you can say, like there are 3 V's which are very common. It's volume, velocity, and variety, sorry about that. And this pipeline extracts the data from various sources and ingests the needed info for the model training, which is only possible once it has been, transformed. It is consumable so that the model will understand. So it could be like, you need to mask some of the personal identified information so that, that information is not fed into the model itself. And sometimes you need to apply some complex transformation. Maybe you have to do some joins, aggregations, and sort of, some specific filtering before it is being, fed into destination sources, and then the model will be able to consume. So again, it does depend upon speeding up the availability of the data for innovation and growth. It also does depend that how the data is formulated, or so that it should be consumable for the machine learning models. And the next up question is, how will you decide which model performs the best, or which model you need to train? Because there is a plethora of models out there. So it certainly depends upon certain parameters, And also, it's very common that we say that ML looks like a black boxes, and the results are like too hard to explain, regardless of how good they are. So you need to understand, like certain parameters which are important before training any kind of a model. Firstly, of course, is performance, because it's it's directly proportional to the business use case that you are trying to solve, or the implementation. Then explainability is also a vital concept. Are the interpretation of can you understand the results which is the model is producing? And next up is complexity, how complex that model is. The more the complex a model will be, harder to explain, it will be harder to be intuitive. And of course, it depends upon the size of the data set. For example, the deep neural networks, they require like tons of data, while KNN, which is the K nearest neighbors, it can work even on the smaller data set. So entirely depends upon, there are, I would say, like the crisscross of all of these parameters in order to choose which model will, which will be better for your use case. And next up is dimensionality. So this, dimensionality is like this. There is a number of features. If you have more number of features, or the size of the data is huge, if it is like higher dimensional data set, can you create it? Can you do it as a lower dimensional? Because again, there are some dimensionality reduction algorithms like PCA-TSNE, but not every model scales well with the high dimensional data set. So you need to be considerate about the factor that, dimensionality of the model is important to understand. And training time and cost, it's highly proportional to the budget available. For example, latest in one of the projects which I was doing as a side project, I didn't have the access to certain of the, the VMs or the, all these big VMs in order to train the model. So it does depend upon, how much budget you have, because if you are training bulky data, or if you are training the models on the very large data, you certainly need a lot of resources, and that depends on how much cash you have. And inference time is also depends upon the time to run the model and make the predictions, because certainly some models takes months and hours or days, whatnot. And next up is what metrics to use for model testing. So it depends upon the problem statement that you are trying to, solve. So really, for the classification PRF, that's precision, recall, and F score. Depends upon, okay, these are the metrics, or if you want to do some accuracy, all these parameters that you can use in order to find, okay, this model is performing giving 90% accuracy, so I'll take this model. So it depends upon what kind of problem that you really solve, and then you can track the metrics using the few iterations by using some performance, by having some performance charts or something. And then you need to test on the unseen data set, like the real data set, to check for the error in the loss function. And again, unit testings are always the best. If you want to check about the model robustness on the real data set, then of course unit tests are one such metrics in order to test your model. This entire, the chart over here shows different metrics for every subset of the problem that you're trying to solve. For example, if you're trying to solve the learning models, in the supervised learning, okay, these are certain parameters that, certain metrics that you can use in order to verify or evaluate your model. For example, the supervised learning, precision, recall, F1 score, confusion matrix is one such. Unsupervised has purity and RAND index. For example, for the hybrid model, also you have Turing test, and also SHAP and human versus machine. Similarly, for the statistical and human is in the loop models, you have different other parameters or the metrics that you can use to evaluate your model. And next up, once the model has been trained, data is there, and you have evaluated it. Now you need to package the model. And why do you want to do it? So there are a couple of reasons. After the trained model has been tested in the previous step, the model, it can be serialized into a file to be exported to the test or the production environment. And that's kind of a, the first parameter which I'm talking about is the portability, because you want to replicate the model in multiple or in the various setups, either in the VM or in the serverless. And when I take, say, like the serialized files, once you have created that, I mean, it does come with some kind of a compatibility challenges. For example, model interoperability, if it is not done right. For example, I mean, why it's a big challenge is, like sometimes the models which are trained on a different framework. For example, there is a model 1 which is trained using the sklearn module, and there is a model 2 which is trained using the TensorFlow. Then the model 1 cannot be imported or exported using the TensorFlow for further model fine-tuning or model inference. So you need to understand, like why we want to package package the ML models. And again, you want to draw the inferences. So the models in the real time check out whether your model is performing best or not in terms of when it is actually not working in the simulated environment, but in the real time. And next is, again, interoperability, which I've already explained, that you want to fine-tune it, retrain, and adapt to various other environments. Okay, over here, I'll just show about the demo because there's a lot of theory which I've covered. And I have used MLOps framework, and over here you can see, again, importing the libraries, creating, a small function about the evaluation metrics, and over here you can see using the MLOps ML Flow framework, which is like an open source framework by the Databricks, and it also use like end-to-end lifecycle management of the machine learning. So over here you can see the first like the couple of lines. Reading the data set, if the data is not available, going in the try and except block, and it has been put in the, like once you are doing the bifurcation of the data, like the train and the test. Now you're training the model and tracking, like once how the model is giving the predictions, like training the model, and then evaluation metrics, all the predicted and the, like the test values will be fed into it, and the RMS, EME, and R2 values will be plotted, and it will be logged. So if you go in ML Flow, like UI, you can see all these evaluation metrics. For example, over here, you can see, okay, that's how the ML Flow UI looks like. On the right side, you can see, the metrics and the parameters, like you can play around with alpha and the L1 ratio, and then you can see what are the metrics. These are the evaluation metrics and which model performs the best according to your condition. And over here, you can see, like how the UI looks like, and of course, you can have some charts which is being plotted in, like you can understand more and more and just play around with it. Next up is the final topic, which is principles of monitoring the ML pipeline. These are the key principles which I know, and like I would love to explain more on that, is when you're monitoring any kind of a machine learning like pipeline. So drift is one such concept which like it helps in checking the degradation of the predictive model performance. Either it's drift, the model is not, either it's, drift is, that concept, it could be a feature drift, or it could be a data, or it could be a model drift. And similarly, we have the bias. So errors which lead to the skewed outcomes, low accuracy, and of course the analytical errors. So if your data is skewed, then of course the model will not be able to, will not be able to understand the exact features, or will be able to make the correct predictions. So, so it highly depends. The bias could be either from the data itself, or either it could be from the model that you have chosen. For example, there is one such paper which I really enjoyed. And that was my first research paper when I started into the research as a career, was man is a programmer, women is a homemaker, or man is a scientist and women is a receptionist. That's kind of a very biased, and that's done by the word-to-vec algorithm itself. And the word-to-vec algorithm is trained on a Google News data set, which is certainly biased. So it depends, if your data is biased, of course, the model will give you the biased decisions. And next up is the transparency. AI in general is non-deterministic. So you need to build the trust in AI systems. And how you build the trust is, like applying some of the algorithms, and also like doing some explainability factors onto it. Like for example, in the explainable AI, it's important to understand the decision, why the model is making a certain decision. And next up, I have a bunch of resources for your reference. And of course, the code and the presentation will be on my GitHub for your later reference. And I really want to thank the organizers and the plethora of the people over here who have supported me and motivated me to give this talk. And I just can't be more happy than ever because it's my first talk at the deserted DevOps Island, and I've been enjoying it.
Thank you so much, Rashmi. That was amazing. And we are so lucky that we got to host your debut. And I hope you go on to other great things.